In this video, we're going to discuss strong versus weak acids and bases. So depending on how good your molecule is at giving away H+, or picking up H+, will make the difference whether you are strong versus weak. Strong acids, the name kind of implies like, oh, it's very destructive. We think of acids as dangerous molecules. But it has a very technical meaning in chemistry. Strong fully dissociates, which means if you have something like HCl, it will 100% turn into Cl- and H+, or as close to 100% as anything meaningfully gets. A weak acid or base, not fully. This is things like acetic acid. So if you have HAC, it will break apart into H+ and AC-, but truth is it's in equilibrium. It can be some percentage on both sides. While our fully dissociated strong acid should be 100% product and 0% starting material, our weak acids and bases can be anywhere in between. They can be somewhere from near 1% all the way up to near 99%. And the reverse would be true on the other side. As a result, when you have a weak acid, there's always a little bit of it still around. And there's always a little bit of your products. And so that equilibrium means that you can adjust it. Add a little bit more to one side. Well, with all equilibrium, if you suddenly have more of one side of the reaction, it moves the balance point and pushes back towards the other side. So we'll discuss weak acids and the complexity of equilibrium with them in another video. For a moment, let's focus on that strong acid. If we have a reaction like HCl plus NaOH, well, they're going to react to make NaCl and water. Beautiful part about a strong acid and base, we can just assume that they do their job. This is just stoichiometry. Like any other reaction, we can presume that all my starting material goes to product. And so if I have 150 milliliters of 1.0 molar HCl and 145 milliliters of 1.01 molar NaOH, and I mix them. Well, I have two real starting materials, so there's going to be a reaction. There's going to be a limiting reagent here. My balance reaction is 1 to 1 to 1, so we could calculate out how much of each we have and figure out which one we don't have enough of. For my HCl, 0.150 liters of the HCl solution. So 150 milliliters. And I need to get out of volume. 1 liter of HCl solution contains 1.0 moles of HCl. So we can find we have 0.150 mole HCl. And if we went and go ahead and do that for the sodium hydroxide, well, I have 0.145 liters of the sodium hydroxide solution. And we were told that in 1 liter of the solution, from its molarity, we see that it has 1.01 mole of the chemical. We will find 0.1465 mole NaOH. Since they're 1 to 1, well, we can see that one of these is less than the other one. Sodium hydroxide is our limiting. And so they'll react. We will use up all the sodium hydroxide, and we will use up that much HCl. Since it's 1 to 1, our amount of HCl, 0.150 mole, is going to react with the amount of hydroxide, 0.1465 mole, and they'll destroy each other. That means I'm going to have a little bit of HCl left. There's going to be a tiny amount of hydrochloric acid left. So 0.15 minus 0.1465, I'm going to find that there is 0.0035 moles of HCl remaining. Well, I had an acidic solution, I had a basic solution, and at the end of mixing them, I have a tiny amount of acid left. So let's think about all those solutions for a minute. Let's look at the pHs of each. If I look at the HCl original solution, well, my pH is equal to the negative log of my H+, and, well, it's a strong acid. If it's 1 molar HCl, strong acids break fully apart. This is really 1 molar H+ and 1 molar Cl- at the same time. And so in that original container, we know the molarity of H+, it's whatever the HCl was. It's the whole idea of a strong acid. So 1.0. If we want to calculate that out, oddly enough, you'll actually find that that is pH of 0, which was the bottom of our pH scale. If we want to do that then for our final container, well, I have 0.0035 moles, and I've got some volume. Truth is, your volumes don't add perfectly, but they're pretty darn close. So 150 milliliters plus 145 milliliters is going to end up with 295 milliliters final volume. This is a bit of an assumption, but they were mostly water in those solutions, so they should mix fairly close to the same amounts. Well, I've got my final volume, and I have my final moles of HCl. And so I can find my concentration. My pH is going to equal the negative log of my H+ concentration, which is moles over liters. So 0.0035 mole over 0.295 liters. Which, if we want, that is the negative log of 0.01186 molar HCl. Which is way less than it started, because we consumed the vast majority of it. There wasn't very much HCl left, and it was in a bigger volume. So by destroying a lot of that HCl and diluting it, we find that there's this much lower concentration of it, but there's still HCl floating around in solution, which means there's still free H+. So if we solve the pH, our pH is now 1.93. It's higher. We got rid of some of the H+, and so it wasn't as acidic. And so our pH has gone up. But we still have a very acidic solution. And this is one of the problems with strong acids. They're really good at massively swinging the pH of a solution. Let's think about that 1 mole HCl again. 1.0 molar HCl, we plugged it in, we said, hey, pH negative log of 1.0 equaled 0. That was our pH. Well, let's scale it down. Let's dilute it, which is kind of what happened above. Reacted some and then diluted it. But let's just put it in 10 times larger volume. So we had 1 liter of 1 molar to start. Let's put that same amount of HCl but into 10 liters. Well, that's going to give us a more dilute solution. When we solve the negative log of our more dilute solution, what we're going to find is that the pH is 1. Well, take that same amount of HCl and put it into 100 liters. And so 1 mole over 100 liters is going to be 0.01 molar. Well, negative log of 0.01 molar, it's going to be 2. In fact, if you keep doing this, 1,000 liters, 10,000 liters, 100,000 liters, what you're going to find is that it just moves our decimal over one time. Every time you divide by 10 again, so you get more volume, you move the decimal over once. Well, because of the way logs work, the log is really telling you how many times do I have to slide my decimal. Remember, log is telling you the opposite of that power. If I'm trying to make 1.0, I want 10 to the 0. If I want 0.1, well, then I need 10 to the minus 1. I need to divide by 10 once. 10 to the minus 2, I need to divide by 10 twice. 10 to minus 3, 10 to minus 4, 10 to minus 5. What you're going to find is that your pH is really just telling you that exponent. That means we're still at pH 5 when we've dissolved it in 100,000 liters. Which means we got to go to 1,000,000 liters to get down to pH 6, and we've got to go to 10 million liters till it looks like pH 7. The reason why the pH is still so great, despite being very little HCl left after our reaction with sodium hydroxide, is that it takes only the tiniest amount of HCl. Because pH is done in these exponent systems, 10 to the minus 6 molar HCl is still an acidic solution. And so when we're up there at, as we calculated, 10 to the minus 2, yeah, the pH is going to be very small. It's going to be very acidic. This also warns us about why you can't dump acid down the drain, or base. If you've ever dumped liquid plumber or Drano down a drain, they are filled with basic molecules. It's extremely basic, and it does a lot of damage to the pipes. They're not actually good to use at home. What's going on is that it takes a massive volume to dilute a strong acid or base enough to not be seen. 1 mole of HCl needs 10 million liters of water before it doesn't look acidic. And so even if you pour just a few milliliters of a light concentration of HCl in the sink, it's still going to take tens of thousands of liters of water that it has to spread out in before it's not noticed. So when acids leak into water reservoirs, it can cause enormous damage as it shifts the pH rapidly. And there's a lot of life forms that need a very set pH to survive. Change it too much, and they start to break down and die. And so plants, amphibians, lake weeds, fish, things like that, they're very susceptible to the runoffs of our strong acids and bases.